During this lesson, what we will be focused mostly will be the structural diagram and the electronegativity. And on the electronegativity, we will discuss what is the electronegativity difference, what is the trend of electronegativity in a periodic table, how to draw the dipole moment, and what is the relative bond strength. Okay, so let's start with the first part of the lesson. So up to now, we have seen the Lewis dot diagram when we were representing the electrons in the outer shell, or on that is known as the valence shell. And we discussed everything, starting with the Lewis dot diagram of an atom, of an ion, the Lewis dot diagram of an ionic compound, of a molecular compound, and then we saw how the single bond, double bonds, triple bonds are formed. We saw the cases where there was not only one central atom in the molecule, but there were multiple central atoms, and then we saw how to draw the polyatomic, the Lewis dot diagram for polyatomic. So we always, when we see the Lewis dot diagram, we see it as the electrons that are represented by dots, okay, by dots. And bonds are in the Lewis dot diagram. Now, when we talk about the Lewis structural diagram, what do we see? Those that are represented by like two electrons that are connected together, two electrons that are connected together, are represented by lines. So the difference between the Lewis dot diagram when we have, let's suppose, when we have any compound, let's say that we have let's say that we have water. So when we draw the Lewis dot diagram for water, the central atom is oxygen, and then we have completing it with 8, and then we have hydrogen here in both sides. So in the Lewis dot diagram, the bonding electrons, the pair of bonding electrons is represented by 2 dots. And then we have the lone pairs, in this case in the central atom only, but we may have the lone pairs even on the other ones. However, when we are talking about the structural diagram, the dots are represented by lines. Okay, so a single line is represented by 2 single bonds are represented by 1 line, double bonds are represented by 2 lines, and triple bonds are represented by 3 lines. Okay, so let's take a look at the Lewis structure diagram of phosphoric acid, fluoride, so hydrogen fluoride. In this case, what we have as the Lewis dot diagram is that the hydrogen is here, and then we have fluorine, 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outer shell. So those 2 electrons are the electrons that are bonded together, so between hydrogen and fluorine. When we are drawing now the Lewis structural diagram, then we go, this bonding here is replaced by a line, and then we represent the electrons that are in the outer shell. So this will be the structural diagram of HF. Now let's take a look at the, let's say, carbon dioxide. When we see carbon dioxide, the formula is this one here. However, the Lewis dot diagram will be something like this. Carbon, and then we'll have a double bond here between one oxygen and a double bond between the other oxygen. And then we will have 1, 2, 3, 4 more for this. 1, 2, 3, 4 more for the other electrons for the other oxygen. So this will be the Lewis dot diagram. The Lewis structural diagram, those bonding electrons will be replaced by lines. So now we'll have carbon, and we'll have 2 lines here. And for the other for one of the oxygens, we'll have 2 lone pairs, or 4 electrons in total, and 2 lines because it is double bonded, and 2 lone pairs in the other oxygen as well. Let's now draw the Lewis dot diagram for nitrogen gas and water. We actually did water, but it's okay. We can do it again. So let's start with the Lewis structural diagram of nitrogen. If we are drawing the Lewis dot diagram, then we'll have triple pair in between the 2 nitrogen, and then we will have 2 electrons more in the other one. However, when we draw the structural diagram, so this is the Lewis dot diagram. When we draw the structural diagram, those triple bonds that are between nitrogen will be replaced with a line. So, and 3, and then each of the nitrogens will have two electrons on the outer shell. And when we are drawing the Lewis dot diagram for water, then for the Lewis structural diagram for water, we have a single bond in between the oxygen and both hydrogens, and then 4 electrons in the other one. So as you see here in the Lewis dot diagram, the lone pairs are removed, and the bonds are represented by lines. So when we are saying just the structural diagram, we don't even care about the lone pairs. So when we draw the structural diagram, then we go just triple bonding between a nitrogen, and then here we will have oxygen 1 hydrogen, and we don't care about the electrons. Okay, so in the structural diagram, we have lone pairs that are removed, and we see only the lines between 2 atoms. So if we summarize this, what we will see is that we have 3 things to know. The first one is the Lewis dot diagram, where all the electrons and the bonding pairs are represented with dots. The other diagram that we use is the Lewis structural diagram. In the Lewis structural diagram, what do we see is bonds, bonding electrons are replaced with lines. And then single bonds equal 1 line. Double bonds equals 2 lines. Triple bonds equals 3 lines. And when we are talking about the structural diagram, so 3, structural diagram, just what we are representing is just the bonds, not electrons in the valence shell. Okay, so keep this in mind. Lewis dot diagram, everything is dots, everything is represented. Lewis structural diagram, the bonds are replaced with lines. Single bonds, 1 line, double bonds, 2 lines, triple bonds, 3 lines, and the structural diagram, we just represent the bonds, not the electrons in the outer shell, not at all. Okay, now you can work on the assignment of lesson 3, where you are representing the Lewis dot diagram, the Lewis structural diagram, where you will show the electrons in the outer shell, and the structural diagram, where you will show just the bonds, not the electrons in the outer shell. Also, I did the session on the previous lesson on those assignments of those columns, so that we were talking about. Okay. Now let's move to electronegativity. Okay, electronegativity is the relative ability to attract valence electrons. Electrons in general, but valence electrons, because those are the ones that we will be willing to move. So what I want you to do now is to complete something that is known as the electronegativity scavenger hunt, and then reply or tell me what are those, answer to those questions here. Between metals and non-metals, which group has the highest electronegativity and which one has the lowest electronegativity? So you have to go to your periodic table, and I will give you like 10 minutes to complete this. And then we will discuss the questions together in class. Based on the definition that we just said, the electronegativity is the ability to attract valence electrons. And now we know that in between metals and non-metals, the one that like to attract electrons are non-metals. And how do you find this number in the electronegativity number in the periodic table? Is if you look at the periodic table, let's say in the case of phosphorus, number 15 is the atomic number, the number of protons in the nucleus. 30.97 is the atomic mass. Atomic mass. And 2.2 is the electronegativity. So when you take a look at the electronegativity, let's say between metals and non-metals, we will notice the non-metals that are above the staircase will have the higher electronegativity, and this is explainable because non-metals, they want to gain electrons. Okay, and now which compound has the highest electronegativity? You will notice that the highest electronegativity is fluorine with electronegativity of 4. So there is no other element that has a higher electronegativity than 4. The element that has the electronegativity of 3.4 is oxygen. Then between carbon and nitrogen, who would have a stronger pull on valence electrons? So now if we take a look, carbon has an electronegativity of 2.6. And nitrogen has an electronegativity of 3.0. So therefore, nitrogen will be the one that will have the stronger pull on valence electrons because it has the highest electronegativity. Using the diagram below, draw an arrow to show what is the direction or the increased electronegativity. So in general, when we move along the periods, what is within a period, what is happening is that the electronegativity is increased as we move from left to right. And then when we move vertically, what do we notice is that the electronegativity is increased as we move from down up. So in general, the electronegativity is in the periodic table is increased in this way, reaching fluorine here, which is the highest one. Okay. So now you can do this in your own. When we see lithium has an electronegativity of 1.1, then carbon has an electronegativity of 2.6. Oxygen has an electronegativity of 3.4. Francium has an electronegativity of, here's francium. I'm not able to find now francium, but you get it now. So you find the electronegativity and then you sort from the lowest to the highest. So francium is 0.7. And then you keep going like this, and then you start sorting them from the lowest to the highest. Now, when we talk about the electronegativity difference, what we will see is the absolute value of the electronegativity of the biggest one minus the electronegativity of the smallest one. So we will see, let's say, the electronegativity between chlorine and fluorine. What do we notice here is that the electronegativity of chlorine is 3.2 and the electronegativity of fluorine is 4.0. So now when we are calculating the electronegativity difference, which is like this, then what we are doing is we are taking the electronegativity, the absolute value of the electronegativity. So this will be, in this case, will be 4.0 minus 3.2, and this will be 0.8. Those kind of lines or parentheses are indicating that the electronegativity has to be always positive. So in mathematics, those are known as the absolute value, which turn every number, either positive or negative, into always positive number. Okay, so now let's see and figure out what the electronegativity difference between bromine and iodine. So bromine has an electronegativity of 3.0 and iodine has an electronegativity of 2.7. So therefore the electronegativity difference, always this triangle here means difference, is the absolute value of 3.0 minus 2.7 equal to 0.3. Okay, the electronegativity difference is taken between the central atom and the peripheral atom. So when we have a compound, in this case, well, we talk about central atom for molecular compound. So therefore, we will see what is the electronegativity difference between the central atom and the peripheral atom. Therefore, the electronegativity difference will be needed to calculate it, electronegativity difference, so EN difference, will be needed to calculate it for every connection between the central atom and each peripheral atom. Okay, let's take a look at this example here. So we have CHClFbr. Okay, so now let's draw the structural diagram of this compound. If you go through the steps that we have said even before, you will see that the structural diagram will be carbon being the central atom, and then you will have, in one side you will have chlorine, and then in one side you will have hydrogen, on one side you will have fluorine, and on the other side you will have bromine. Okay, so now the electronegativity difference between carbon and hydrogen will be whatever is the electronegativity of carbon, that from the periodic table is 2.6, minus the electronegativity of hydrogen, that is 2.2, so will be 0.4. And then when we are calculating the electronegativity difference between carbon and chlorine, then we will see chlorine has a 3.2, so 3.2 minus 2.6 is equal to whatever the calculator is giving you. 3.2 minus 2.6 is 0.6. And then you move to the electronegativity difference between carbon and fluorine. Fluorine is the element that has the highest one, so 4.0 minus 2.6. 4 minus 2.6 is equal to 1.4. And then the last one will be the electronegativity difference between carbon and bromine. So bromine has a 3.0 minus 2.6 in absolute value. So this will be 0.4. So this is how you calculate the electronegativity difference between the in a compound from the central atom to each of the connection that the central atom has with the other elements, other atoms. Now you may say, why would I need to know the electronegativity difference? The electronegativity difference between two atoms and in a compound, it's giving us about convention of the bond strength. What is the bond strength? Is how strong is the bond between the atoms in the compound. The larger the electronegativity difference between the atoms, will result into a greater strength bond. So the larger electronegativity, the stronger the bond. Okay, so let's take a look now between the electronegativity difference between sodium and chlorine. And again, we will see the periodic table. So the electronegativity difference between sodium and chlorine will be the absolute value of 0.9 minus 3.2. And this is an example of the fact that what we are considering is, even though that this is negative, the absolute value makes us to have a positive value. So for chlorine is 2.3, and then for next one is oxygen. So electronegativity difference between the two oxygens is 0, because 3.4 minus 3.4 is equal to 0. So this will be 0. And then we have aluminum chloride. So aluminum, the electronegativity difference between aluminum and chlorine will be 1.6 minus 3.2 equals to 1.6. So this will be 1.6. And then we have tetraphosphate decoxide. So the electronegativity difference between phosphorus and oxygen. Phosphorus has an electronegativity of 2.2 minus oxygen is 3.4. So this will be minus 2.2, 1.2. So this is 1.2. And then electronegativity of sulfur, we have atoms of sulfur, 8 in this case. That means that the difference between the two atoms is, electronegativity difference between two atoms is 0. We discussed the carbon and oxygen, which is 3.4 minus 2.6. It's 0.8. And calcium and fluorine will be 3, because 4.0 minus 1.0 will be 3.0. Now when we are sorting them, or when we are ranking them from the strongest to the weakest one, the strongest one will be calcium chloride, then sodium chloride, then after that is aluminum chloride, then will be carbon dioxide, then will be tetraphosphorus decoxide, and then after that we have oxygen and sulfur. Okay, so when you are sorting them, it's just sorting some decimal numbers. When we are talking about the dipole moment, what we are identifying is the direction of the electron distribution. So now again, let's rewind it for a bit and then we will see. The electronegativity is the ability, the relative ability of the atoms to attract electrons. If we have an atom that is able to attract more electrons, what will happen in the compound is that the electron will spend more time into this atom that is able to attract more electrons. In molecular compound, what is happening is that the electrons are shared. However, they are not always equally shared. The cases where some of the atoms have a higher relative ability to attract electrons than the other atom, then what will happen? The electrons will spend more time into that atom. So now this is shown by the dipole moment, which is the net direction of the electron distribution. The higher the direction of the dipole moment is the same as the direction in which the electrons are pulled. The dipole moment, keep in mind, is found only in polar covalent bonds. Okay, what are polar covalent bonds? Keep in mind what we have said. The ionic bond is formed between metal and non-metals. Metals have the tendency to lose the electron. Non-metals have the tendency to gain the electrons. By losing and by gaining, what is happening? We have two entities that are with opposite charges, which will create that is known as the electrostatic force between the two. Okay, so electrons in the atomic bonds are shared. And the electronegativity difference between the electrons is greater than 1.7. The bond strength is the strongest one. Now, when we have a polar covalent, the electrons are not shared equally. So what is happening in this we will have on polar covalent, what is happening, we will have a dipole moment. So one of the atoms has a greater ability than the other to attract electrons of the valence share. So, and as a result of this, the electrons will not be shared equally. Unequal share is happening. The electronegativity difference is between 0.5 and 1.7. And the bond strength is somehow in the middle. When we have non-polar covalent, meaning that the two atoms have pretty much the same electronegativity, then the electrons are almost equally shared. And the electronegativity is less than 0.5. What is happening in this case is the bond strength between elements or atoms is the weakest. So the 1.7 is 0.5 is the cutoff of of the bond strength. Whatever is above the 1.7 is considered to be ionic. Whatever is between 0.5 and 1.7 is considered to be polar covalent. And whatever is between 0 and 0.5 is considered to be non-polar covalent. Okay, recall here what we have said about molecular or covalent compounds. What are bonds and what is the electronegativity? Molecular or covalent compound are where the electrons are shared between two atoms, but on some cases they are not equally shared, and on some cases they are equally shared. When they are not equally shared, what is happening is that is formed that is known that is non-polar covalent bond, and when they are almost equally shared, then what is happening is a non-polar covalent bond. Now, in the non-polar covalent bond, electrons are almost or exactly equally shared. So when we see, let's say, CS2O2, and in general, all the ones that are polyatomic elements are non-polar covalent bonds, and the one that has an electronegativity difference of between 0 and 0.5. This is the classification. And when we talk about the polar covalent bonds, the electrons are not shared equally. Between the two nucleuses. Let's take a look at FBr. Okay. Now, see what we have here. The electronegativity difference between fluorine and bromine will be 1. Okay. So now, what we notice here is that the fluorine is having a higher electronegativity, will have more electrons in the valence share, by making it slightly more negative than bromine, that becomes now in relation to fluorine, it becomes like a positive, quote unquote, positively charged. This slight difference between the two atoms in the polar covalent is identified with the Greek letter delta. So when we have delta negative, means that the electrons are more attracted toward the nucleus of this atom. Toward the nucleus of this atom, and making it slightly more negative than the other one. Than the other nuclei. Now, delta positive indicates that delta positive indicates that the electrons are spending less time in this atom, in this nucleus of this atom, okay, in this atom. So they are being kind of pulled away from, okay, yeah, they are being not equally, they are being pulled, yeah, pulled away from the nuclei of this atom, which makes this slightly more positive than the other nuclei. So this, the fact that we have a delta negative here tells us that what we have actually is a dipole moment in which the electrons have the tendency to stay more into fluorine. So this is how we write the dipole moment. So now you can continue with the assignment on lesson 3. What you will see is what is the electronegativity difference, and then you will draw the dipole partial charges, delta positive, delta negative, and so on. Okay. Before you start completing this assignment, I will show you one more example. So let's suppose that we have SH2. Okay, the structural diagram for SH2 will be S is here, and then we'll have hydrogen, hydrogen. Okay, so now when we see the electronegativity difference between sulfur and hydrogen, we'll have a 0.4. Okay, so a 0.4 means so that we will have 0.4 toward the sulfur. So sulfur will become slightly negatively charged, leaving the hydrogen positively charged, negatively charged, positively charged. The dipole moment will be this and this. And the net dipole moment will be something like this. Or when we have, let's say, HCP. Okay, carbon is the central atom, and then we have hydrogen in one side and phosphorus on the other side. Okay, so now the electronegativity difference between carbon and hydrogen will be 0.4. Okay, 0.4 with which means that carbon is becoming slightly negatively, and hydrogen is becoming slightly positively charged. When we move to carbon and phosphorus, so it will be again 0.4. So now phosphorus is 0.2, 0.4, so we'll have 0.4, which means that carbon will be slightly negative, and phosphorus will be slightly positive. Okay, so now in between those two, the net pole, when you have 0.5 going in this direction and 0.4 going on this direction, then net will be 0.1 on this direction. And this will be the net dipole moment.